In this video, we're going to be talking about the building blocks of deep learning. These are the very most basic parts of a deep neural network that we're going to talk about today, and we'll be building on these as we go through the class. So, it seems like a good place to start would be to talk about what exactly a neural network is anyway. So there are these things called neurons. They're sort of the atomic unit of neural networks, the very most basic part. And then a neural network is a network that connects multiple neurons together in typically a directed acyclical graph, a DAG. But sometimes there'll be loops, and we'll talk about that later when we get to recurrent neural networks, where we put loops in our network for memory. All right, so this is sort of my definition screen that helps you understand sort of the terminology I'll be using. The circles are neurons, and I'll talk about what goes inside of a neuron next. Neurons are arranged in a graph, as I had said. We have at least an input layer and an output layer. And then the whole idea is that we stack all of these neurons together so that they are sort of piecewise learning really, really complex functions that can map our inputs to the outputs that we care to predict, which is what machine learning is all about. Inside of each neuron, there's a linear function, and this linear function looks something like this. For every input that you might have into your network, that input is paired with a coefficient. Here I'm using theta 1, theta 2, theta 3 per convention. If you're of the statistician bent, you might use beta instead of theta. If that's the case, you're wrong. It's theta. Anyway, theta. So we pair the thetas with the x's. We add a bias term, and we get some output z. And this is sort of our linear activation function, or I'm sorry, this is our linear function for a neuron. Every neuron has a linear function. The very most basic neural network is the perceptron, which is really just a single neuron. Invented in, I don't know, I think the paper came out in 1949, but the guy that built the machine was called Frank Rosenblatt, and I think that was in 1957. So he built this thing called the Mark I perceptron machine. It was hardware, actually, that did this function. It really blew everyone away at the time. It was probably the first time people were really afraid that the computers were going to take our jobs. Right, so the perceptron is a single neuron, if you will. You have the inputs, x1, x2, x3 in this case. They're paired with the thetas, as we talked about before, and you project it to some output space. If you were able to find some ideal numbers for theta 1, theta 2, and theta 3, you would build a function that can map the inputs to the output that you want to predict. The perceptron had a really interesting shortcoming, though, and that is there are some functions that are just nonlinear in nature, and kind of the canonical example for that would be the XOR gate. The XOR gate, I'm showing it to you kind of down here. I'll move my mouse. What you can see is, here, I'll even turn the pointer red. Yeah, look at that. So x1 and x2, if x1 or x2 is 1, but not both of them, the output will be 1. And if we graph that, you can see that at 0, 0, the output's 0. At 1, 1, the output's 0. But at 0, 1 or 1, 0, the output is 1. Right. So there's no way to linearly separate these two cases, right? You just can't do it. This is where the perceptron falls apart. It's not possible to solve this really simple equation with the perceptron. So that's where we come up with this idea of sort of stacking perceptrons, or making a network of perceptrons. And the idea here is that when you have multiple layers of them, they can all learn kind of a part of a really complex function, sort of piecewise. There's one problem with what I've described so far, though. If you take neuron 1, which maybe is represented down here, z1 equals x1 theta 1, x2 theta 2b, and then you take neuron 2, which is the output z2, x1 theta 3, x2 theta 4, and you roll them all up into and then you say, okay, I'm going to feed these up into another neuron, what you really end up with is just a really kind of bigger linear equation. So you can't really still solve that XOR problem. So we have another piece to the neuron, and that part is the activation function. An activation function goes between the linear functions in neurons to create a nonlinearity so that they can model those nonlinear interactions. The most common and probably the oldest is the sigmoid function, which you might remember from logistic regression. The sigmoid function is kind of neat in that if you give it a really, really negative, it'll constrain the output to 0. And if you get a really, really big number, it'll constrain the output to 1. And then you get kind of this sigmoid function in between where you create this nice nonlinearity. This allows the neural networks as they're stacked, or I'm sorry, the neurons as they're stacked upon one another to learn these nonlinearities. There are a lot of other activations, and it turns out that some of these are better for neural networks. The first one, and the one that you'll see me sort of defaulting to, is called ReLU, or rectilinear activation. And how this works is it just takes the maximum of either x or 0. And the reason people like this one is it's really easy to compute and it's really easy to differentiate. What? Calculus? Yeah, we'll get to that in a second. And then the other one that I also like is called hyperbolic tangent. And hyperbolic tangent's really nice because it kind of keeps things around 0. And it squishes things sort of between there, but it has kind of a wider space than sigmoid. This is actually also very beneficial when we're training, and that'll become obvious later. Anyway, sigmoid, ReLU, tanh, all nonlinear activation functions. So then what you need to remember is a neuron has two parts, a linear part and an activation. Inputs come in, we apply the linear function, we apply the activation function, outputs go out. Simple, right? Multilayer perceptrons then are special stacks of neurons. And we arrange these in layers. The first layer is the input layer. Second layer is the hidden layer. Third layer is the output layer. Now you don't have to have one hidden layer. You can have any number of hidden layers. But in the classical multilayer perceptron, it's a single hidden layer. Theoretically, so then what is this class that you signed up for about deep neural networks? Well, deep neural networks, I'm going to define this as networks with more than one hidden layer. So this is not a deep network, but if we had two hidden layers, it would be a deep network. Now you could say, well, I think that the threshold of deep neural networks is that it should have 5 hidden layers, or 50 hidden layers, or 100 hidden layers. We can come up with all these arbitrary thresholds, and I've heard people do that. The result of that is a nerd slap fight. No one's right. Who knows? If it has more than one hidden layer, I'm going to call it a deep neural network. Why are we doing this? Why aren't we just using random forest or one of these other really good machine learning models that is maybe less complex, less crazy? So deep neural networks have a few really important advantages. This is sort of the motivation to why you would care to learn them. The first one is automatic feature engineering. When you have stacks and stacks of neurons kind of in this sort of deep network, what happens is every layer of neuron can learn a new more complex function that builds on the learnings of the neurons that came before it. So it kind of gets to learn more abstract, important features that are further and further away from the data. This automatic feature engineering is really nice because it takes the place in a lot of cases of some of the things that we would have to sort of code by hand in feature engineering for other machine learning methods. The other thing is that you can really handle very complex inputs and outputs. There's no known model that's as good as the deep neural network for processing images and text. Neural networks in this case are really the king. They don't mind being flooded with lots and lots of information, lots and lots of inputs, whereas a lot of models might not be quite as robust to having, thousands or tens of thousands of inputs. Neural networks, that's sort of their sweet spot. So let's talk about some of the disadvantages. We have no way right now to interpret a deep neural network. If you can, imagine going back to that first equation that I showed you, what is the interpretation of theta 3 in the first neuron? Well, maybe you could come up with some well, that's sort of related to x3, but think about how would you interpret theta 3 on the third neuron in the 5th layer? There's no interpretation to it. These become a complete black box. Maybe you like that, maybe you don't. If you want raw predictive power, deep neural networks are the way to go. If you want explainability, not so much. That's an emerging field in sort of the study of deep neural networks. The next thing is that deep neural networks can be really complex. They can have millions of parameters. It makes them data hungry. They need a lot of inputs. And it also makes it so that I feel like you as the modeler need to justify the complexity. Why are you using the deep neural network instead of the logistic regression? You should be able to say, well, this one does this much better of a job than this one. Lastly, GPUs, right? So GPUs, graphics processor units, are special hardware that allow us to do the math that's required in these deep neural networks to have millions of parameters in sort of reasonable time. You can do on a GPU in minutes what you could maybe do on a CPU in months because there's so many more processors. GPUs are responsible for sort of the revival of deep learning coming since about 2012 on. GPUs have also become a requirement for doing deep learning, and they're expensive and they're hard to use in some cases. And so that's a big downside in my opinion. GPUs get cheaper. They're getting more accessible because of cloud. So we're getting over some of those boundaries. Just the same, GPUs are an important consideration. All right, that's it for this lecture. In the next lecture, we're going to jump in to building a multi-layer perceptron from scratch. We're going to look at how it works, and we're going to learn forward propagation and backwards propagation. Thanks.